It refocused out, didn't it? No, it didn't. Okay. Our capacitance. Okay, so there's a new this new concept here of capacitance, and so we're going to set the stage a bit. If we have two charged conductive amoeboids, right? And okay, and so we have one here that has a positive Q, and then we have another one over here. But we have, so what we've done is if we create a separation of charge, okay, somehow we were able to get our negative charge that was on here, you know, what was making the negative, you know, our electrons. We have an abundance of electrons that was from here over here. So these two things are going to have equal charge. All right, and yeah, count them, they're equal. These two things have equal charge. Okay, we call this a separation of charge. All right, and between these we of course have our electric fields that go straight across, and we have, remember, if we're drawing our field space, okay, it kind of looks like this. Okay, and so on. This is our electric field. Sorry. Okay, so if this is our electric field, it always flows from positive to negative. We always have our lines, and remember, field lines never ever cross upon pain of death. No, not true. We don't cross the streams because of the total protonic reversal. We will debate the validity of having an all-female Ghostbusters revival cast at another time. Although I think I'm totally for it, because I think who they have cast for is freaking amazing. So another way to think about our potential is the work it takes to go against our field lines. So if we take a test charge right here and we work it back in that direction, okay, then we'll have the potential difference. Right, the change in our potential is going to be the potential difference between here and there, right? Okay. Oh, and by the way, capacitors are always systems with no net charge. Okay, capacitors are systems with no net charge. All right, so here's how we define our capacitance. Okay, and it's related to our potential energy. In fact, it's what capacitance is. It's the ability for something to store an amount of electric potential. Okay, it is something's capacitance. So our capacitance is going to be this. Okay, it is given by the variable C, and it is defined as the amount of charge divided by the potential difference between your charges. Okay? Okay, so it's Q over C, and it's always positive. So you can we don't really throw the absolute value in there. We just say that it's always positive, because it's always based on the separation of a positive and negative charge. So if you're paying attention to a positive test charge, then it's always just positive. Yes. Defined as. Okay, that's not squiggly. Okay, that's equal. That's congruent. 3 lines is defined as. Okay. What? If something is defined as something else, then it is implied and included in that the two statements are equal. Because there are other things that capacitance might be equal to. This is a more specific. This is the definition of capacitance, is our charge divided by our potential. Okay. The units for this, we have new units, or we have a new unit that we need to remember. Okay. Our unit for charge is coulomb. Uh-oh. Hope you guys may see a future pitfall here. Our unit of charge is coulomb. Our unit of voltage is the volt. Okay. The coulomb per volt is defined as a farad. Okay, which is named after the little short person king in Shrek. No, I'm kidding. That's Farquhar. No, a farad is named okay. The farad is named after, of course, Michael Faraday. Okay, that unit has the abbreviation F. If you actually have a capacitor that is exhibiting a 1 farad capacitance, you have stored a ridiculous amount of charge at a very high potential. Okay, you're dealing with a whole lot of potential energy there if you have a 1 farad capacitor. For practicality's sake, in our electronics, day-to-day electronics, we deal with stuff in the microfarad to picofarad range. So the 10 to the negative 6 to 10 to the negative 12th range. Okay, there are nanofarads also, but usually it's micro and pico. Alright? Okay, now, here's the trouble. And this is a common pitfall that you guys need to avoid. This is coulomb. Our unit of capacitance is a coulomb per volt. Volt with a T, not a D. Volt. Do not confuse this C, which stands for capacitance, which is the variable for capacitance, with the unit coulomb. That would be bad. All right? So make sure that you are taking into context whether or not you are talking about a quantity, or you're talking about a unit, or you're talking about the variable.
Same thing happens with the volts.
Yeah, volts and volts are similar too, except at least they're the same. They're talking about the same thing. C and C are talking about 2 different things, so we need to keep track of that. Okay, so what we're going to do, I'm going to give you guys a couple of examples of capacitors. But what I want you guys to keep in mind when we're going over this is our capacitors are defined by 2 things. Okay, the capacitance is defined by by constants of nature. Okay, K, or 4 pi epsilon naught, that sort of thing, and the essential geometry. Okay, so in other words, the things that can change once you establish the shape of what you're dealing with, it's what can change with that shape. So we're going to start with a sphere. Oh. Yep. Okay. Okay, our sphere is of radius r. Okay, it has a total charge Q on it. Okay, and that means that we have field lines that are shooting out. Each positive gives off its own field line. They are all radial to our sphere because the surface itself is uniform and it doesn't cause a whole lot of discussion like an ununiform surface. All right. So in this case, our capacitance, okay, or in all cases, our capacitance equals Q over our change of potential, right? So we take some object from way out here and we bring it in, okay, and so that's, you know, from infinitely far away, we come in and we come close to our conductor. Okay. But what then is our potential difference if we're coming from a distance far away?
It's just a V.
Okay, it's just V, but what our V equals, all right, so let me move this, our V equals KQ over R, right, because that's the radius of our thing, right? So the potential right here on the surface is KQ over R, right? Okay, so our V then is really, if we take it from infinity, our V then is KQ over R, and this becomes Q over KQ over R. Yeah? Our Q's will cancel, and this becomes R over K. Now, what is the only variable that can change when you're talking about the size of a sphere? It's the radius. It is the defining size characteristic. In fact, it's the only defining measurement whatsoever of a sphere. Everything is based on the radius. And so the essential geometry of a radius is essential geometry of a sphere is the radius. Now, this can be written as R over KE, or this is the same thing as 4 pi epsilon naught R. And there we have our fundamental constants with our essential geometry for our sphere. So the capacitance at the surface of a sphere, or the capacitance of a charged sphere, okay, is 4 pi epsilon naught R. And it doesn't matter what the charge on it is. Okay. All right. Now, that's for a sphere. We're going to move on, and we're going to do...
He's making a word.
All right. The next one we have then is the most common one that you guys are going to see, which is a parallel plate capacitor. Am I on the screen?
Yeah.
Okay. Now, I'm sure you guys have come across things. I'm sure you guys have come across things that have been really inappropriately named. Okay, in various versions of physics or other things in science. It's just that the name actually it's either a misnomer or it has nothing to do with what we're talking about. This is quite possibly the most perfectly named thing that I've ever come across in science. Okay, because it is literally two parallel plates. Okay, you take two flat surfaces of a capacitor, okay, they should be the same area, although I didn't draw them that way. Okay, and behind it, we hook this up to a battery. Okay, here's our parallel plate capacitor. Okay, on one side of our parallel plate capacitor, and we'll call this positive and negative here, we have a collection of positive charge. And what the battery does for us, or the electric cell, or whatever you want to call it, I'm going to call it a battery because I don't like calling it anything else. Okay, establishes a situation where we have an equal amount of positive charge and negative charge on our plates. Okay, question?
Yeah, let's see what it's
Okay,
It's a pretty detailed
pretty detailed battery.
battery.
It's a 12 volt. All right. It's like a car battery. Okay. So what is our essential geometry of our situation here? Okay, we have two plates, and if they're parallel, okay, so they have a distance between them, okay, and what's that? Right, we don't want the plate. They're held in place. We don't, but the distance between them can change for any particular measurement. Okay, they're going to have equal charge, but is that necessarily geometry? Okay, but they have equal areas, and so our two essential parts of our geometry are the area of the plates. Now I could have any shape. In fact, the shapes don't really matter. Okay, so long as the areas are equal to each other. So I could draw a square, okay, with the shape, and if I drew an amoeboid with an equal area, we're cool. All right, the shapes themselves, as long as the areas are the same. Okay, so what we're going to do is we're going to figure out our voltage. Okay, let's figure out our delta V. So we start with, because we need to start with our fundamentals, V equals negative integral E dot ds. Now, luckily, you guys can tell that our field is uniform going across, right? And so our E dot ds is just, well, it just winds up being delta V equals E d, right? Where if our distance.
Is it not negative?
Yeah, but it doesn't really matter. The negative is going to go away when we do our capacitance, so don't worry about that so much. Okay. Well, now we know that our capacitance, though. Where do I want to write that? I want to write it down here. Our capacitance equals Q over delta V, right? So we have a substitution to make. We're going to take our ED and plug that in here. And so we're going to make a capacitance equal to Q over our field times the distance of separation. Yeah? Okay. But, and here's where we're going to set the Wayback Machines to the very beginning we were talking about electric field. Okay, the electric field for a plane, right? So if we have a plane distribution, a planar distribution, our electric field equaled sigma, which was our area charge distribution, or area charge density, divided by epsilon naught. If you don't remember this, go back and do a little research. Remember that this was, we solved for this one some time ago. Okay, well, this way? Okay. This is coming in here. So now our capacitance is Q. Well, what's our sigma? Our sigma is Q over A, right? That's our charge per unit area. So this becomes, our E becomes Q over A epsilon naught, yeah? Well, let's not plug this in here. Let's plug this one in there.
Wait, wouldn't the epsilon not go to the top of the numerator? Or you go to the numerator?
Not yet.
No, but you just plugged it in.
If I plugged Q for A in for sigma,
Oh, okay.
okay, I haven't got there yet.
Yeah.
Oh, yeah. Okay, so E comes in here, and now we get Q over our field. Yeah? And now we start canceling stuff. Q cancels. And we're left with the capacitance of our permittivity of free space, which, do you remember what this was? What the permittivity of free space really was? It was the ability for charge to travel across a vacuum. A over D. And all of a sudden, fundamental constant, essential geometry. Yeah? Okay. So let's think about this. What happens if we make our plates bigger, if we increase the area? Okay. If we make the area bigger, okay, and we have another one that comes out, right? What are we able to do if our area is bigger? What can we store? Okay. Now, mind you, if the voltage is the same, but the areas are bigger, that means we can store more charge on the plates. Yeah? And then minus is over here. Okay. What if we change the distance between them? Okay. If we get closer, if our distance across, what happens to the voltage is the same. If we get closer, what happens to our field? Field gets smaller, right? If this goes up, field has to go down to maintain the same potential. All right, which also makes sense because D is in the denominator, right? So we divide by, if this number gets bigger, our capacitance gets smaller.
Wait a minute. If D gets smaller, what capacitance do we?
That's what I said, yes.
Yeah.
That's what I meant. If D gets smaller, our field drops. Okay, but it divides here to make our capacitor bigger. Capacitance bigger. Okay, we move them. Oh, I just described it wrong. If our D increases, if our D increases, our field drops. Capacitance. Right? Field decreases. D increases, field decreases, so potential has less charge on the plate, so the capacitance decreases. Okay, so this is the crucial idea there. Okay, that as decreases, our field increases. As D decreases, our field increases. Yes.
So the battery has nothing to do with the total capacity.
No, it has nothing to do with it.
How fast it would
Well,
get it,
sort of.
how fast it reaches its full.
The battery has a little bit to do with it, and we haven't really talked about what a battery really is yet. But a battery is a circuit's ability to boost potential. So what the battery does is it creates a potential difference between the two sides of the plates.
So it turns potential to potential. Is that
No, if there's no battery, there's no charge on either plate.
okay?
Okay, the battery essentially sucks electrons from one side and plants them on the other. It forces a shift in the electrons in the circuit to go to one side of the capacitor over the other.
What you just
Generally through electrochemical processes. which are somewhat beyond the scope of this course. Okay. Yes, if there was no battery, there would be nothing causing a potential difference. Okay.
When we solved for the electric field, which is rho over epsilon naught, was that
Sigma, but yeah.
Yeah, was that for, since for one of them it's rho over 2 epsilon, so since we have 2 of them, the 2 crosses out, right? So how-
That is for if we have a two-sided plate. We only have these are conductor. This is a conductor. The charge is only going to be on one side, right?
Okay.
Oh.
Okay. Over here we have a negative charge on the other side, so the charge is going to be on facing each other. They're not going to there's not going to be any charge on the other side of the plate. Okay, that is the end for that lecture.